Hello, good evening to all of you, and welcome to Unacademy. Welcome to the session of NCRT, where we are covering the entirety of the portion of your NCRT from the relevance of the prelims as well as the mains examination in as much detail as it is required, and in certain areas going beyond that as well. Now, we will be discussing the portion of volcanoes. Now, in the first session, we had discussed about the origin of the universe, the solar system, as well as the case of the origin of planet Earth by the accretionary theory. We also touched upon the evolution of life thereby. In yesterday's session, we basically talked about the interior structure of planet Earth and also dive deep in order to understand the case of your earthquakes, how these seismic events occur, where do they occur, and also the property of the seismic waves. Now, today, we are going to further proceed ahead with the discussion, and we are going to discuss in the same third chapter of NCRT from the book Fundamentals of Physical Geography of Class 11th. You will find the volcanoes, and this is a chapter which is important for your mains examination. You have questions which have been asked in the mains examination for the GS, for the optional as well, and the questions have been known to be repeated. So that is why it becomes very, very important. Now, we will cover line by line of the NCRT book. So, in case you have the NCRT book, you will be able to match that with this also. And the annotations of the PDF, you will be able to find that as a note for the in the description which is provided. The link is provided in the description of the video itself. You will be able to find the annotations of the PDF as well. Use that for the revision exercise. So, when we talk about the case of volcanoes, volcanoes are a geographical phenomena which are quite unique. In fact, one can argue planet Earth does not have any other feature which is as visualistic appealing as is the case of the volcanic eruption. And this volcanic eruption is not something which is absolutely new, by the way. When we were discussing about the evolution and formation of planet Earth, we had discussed that in the entire phase of evolution, there was a time when the planet Earth was basically dotted with hundreds and thousands of volcanoes on a daily basis. Even today, every year, different parts of planet Earth, they experience this volcanic eruption. Now, you would have had some idea about these volcanoes even since you were kids, right? Now, when we were in school, or when you would be in school, you would be hearing about, reading about the volcanoes and wondering where do these materials come from. Initially, one gets an idea that, okay, the core is molten. So, volcanic eruption would be from the region of the molten core itself. But yesterday, we introduced ourselves to the region of asthenosphere. So the molten materials of the volcano, they are provided from the region of the asthenosphere as well. Okay. So let us dive deeper into this case of volcanoes. Let us try to understand their properties in greater detail. Now, this is the page number. Page number 23 is where you will find the initiation of the portion of the volcanoes in chapter 3 itself. Now, basically, when we talk about a volcano, what is it? In simplest of the terms, emergence and eruption of materials from interior of the earth to the surface, that is what is referred to as a volcanic eruption. Now, a volcanic eruption can basically happen anywhere, wherever the land surface, let's suppose, is very weak, and provided in the interior you have the presence of molten materials. These molten materials can crack through the surface and can pour out molten liquid, and that liquid will eventually very quickly solidify to form a kind of a volcanic eruption. Okay, we will basically take a look through the animations and try to understand the various different aspects of a volcanic eruption. Now, whenever a volcano does erupt, the molten materials emerge onto the surface. Okay, whenever that eruption does happen, the molten materials, they emerge and erupt onto the surface, right? Now these molten materials, they will solidify. Why do they solidify? Because they cool down. And as they cool down, they form very hard rocks. Very hard rocks. Okay. Now, these rocks, because they have been produced from something which was on fire, right? So, something which was burning. That is why the rocks produced from this activity, they are known as your igneous rocks. Igneous referring to fire. Okay. Now, these igneous rocks, think about it and apply your logic once, because UPSC had asked this as a direct question in the mains examination. So when the planet was getting created, at that point of time, you could have endless amount of these molten materials erupting from different parts of the planet, and they would have solidified and formed the first types of rocks the planet had ever seen. So that means, by deduction, igneous rocks are the first kind of rocks that anywhere you will witness across the planet. Over a period of time, they might have got changed into sedimentary, metamorphic, etc. That is why these are also what are referred to as your primary rock systems. Primary rocks. Now, you will also come across a terminology such as igneous rock provinces. What does that mean? That basically indicates those kind of areas where this volcanic eruption has created large beds and large sections only of the igneous rocks. For example, in India, you have the region of Jharkhand, some parts of Odisha, Chhattisgarh, Maharashtra, Karnataka, parts of western and southwestern Madhya Pradesh. All these are a result of the volcanic eruption. They have been created as a result of volcanic eruption itself. Now, if you have the breakdown of this volcano, if you analyze this volcano, let's suppose we have a cross sectional analysis. This is a schematic representation. So, molten materials from the interior, they slowly and steadily rise up, and then they will break through the surface. Okay, they have to blast through the surface because you have the solidified rocks there. So that is why they require immense amount of power. Now, this molten material, when it is in the interior of planet Earth, it is known as magma. So the same molten material, when it emerges onto the surface, it comes onto the surface, we refer to it as lava. So lava and magma are almost one and the same. The only difference being that magma is the molten material in the interior, lava is when the same molten material comes to the surface. Okay, that is the only difference. Now, in the interior of planet Earth, up to a depth of from 160 to almost 400 kilometers, right? In those areas, in certain particular sections, you have large accumulation of this molten material. Why do these get created and which sections have this molten material present? We will study that when we read the plate tectonic theory in the coming chapter on Monday. But till then, here, basically, when you have this molten material in large sections in a particular region, that is known as magma chamber. So your magma chamber becomes the supplier of molten materials which break through the surface. Okay, slowly and steadily materials will solidify, and that will form the igneous rocks and even the volcanic cone. But along with that, any volcanic eruption leads to expulsion of huge amount of material, from ash cloud to the case of these small particles which are known as the volcanic bombs, the lapis, all of them, tephra, that is also emitted whenever you have this volcanic eruption. So this is basically the schematic of a volcanic eruption. So here you will observe basically that you have a large eruption cloud. Okay, eruption cloud, I will show it to you with the help of an animation how big it can actually become. In certain volcanic eruption, for example, you see, when you had the volcanic eruption in the region of Indonesia, western coast of Indonesia, you have the famous Krakatau eruption. That Krakatau eruption did occur in the 1880s. The eruption was so massive and the ash cloud created was so huge that it managed to block the sunlight in the region for continuous 2 months. Sunlight could not penetrate. So that is how thick this ash cloud can get. And this can go very high. For example, as recently as in 2022, in southern Pacific, you basically had an eruption which was known as the Tonga eruption. Now, in that Tonga eruption, I will show you the images of Tonga eruption also. In that Tonga eruption, the ash cloud managed to reach a height of 100 kilometers, penetrating through the troposphere, stratosphere, the ozone hole, and reaching up till mesosphere. So, this ash cloud is very, very massive. Now, this ash over a period of time tends to fall down and gets deposited on the surroundings also. That is where all the plants, they will have the leaves on which the ash will get deposited. The leaves, their pores get blocked. Many of the plants, they die. But do you know one interesting aspect here? This volcanic ash, if it is spread very thinly over the soil, over a period of time, it leads to fertility of the soil. The soil becomes more fertile because so many different minerals are added. The soil basically ends up becoming much more fertile. That is why in major volcanic islands, you will observe that the trees are very massive, right? Lot of vegetation grows around. Why? Because of that volcanic ash. But in the short run, you will have the trees to be dying. Okay, the ash cloud can be disastrous. Sunlight is also not available, pores are not also available. This is why the extinction of dinosaurs was actually accelerated. All of us would be aware about the fact how the dinosaurs died. It was because of an asteroid hit across planet Earth. But when that asteroid hit the planet Earth, there were so many series of volcanoes which erupted across the planet, basically because the stability of Earth was disturbed, that these volcanoes almost covered the planet. The plants begin to die, and once the plants will die, the herbivores will die, the carnivores will also die. So that is the dangerous aspect of this volcanic ash. Now, in any volcanic eruption, rock fragments, solidified blobs of lava, cinders, dust, water vapor, gases, all of them that was released, they are collectively known as pyroclastic material. Okay, they are collectively known as pyroclastic material. This becomes relevant for your prelims. Okay, so what are pyroclastic materials? These are basically the different types of fragments that you have which are emanated out of a volcanic eruption. Now all the fragments are not same, by the way. There is a classification thereby also. For example, the particles which have a diameter of almost 2 millimeter, they are classified under the category of volcanic ash. Okay. Then up till around 6.5 centimeter or 64 millimeter, that is classified as lapilli. Okay. And then even larger, you will have them as volcanic bombs. Now, in various different places, you will observe that various different places across planet Earth, you will observe wherever volcanic eruption has happened, there volcano tourism also takes place. Now, in these volcanic areas, you will observe that these bombs are actually sold as a kind of a tourist enterprise, and there's a large industry which is behind this also. Okay. Now, here, this is the representation of the ash cloud which was created during the Tonga eruption. Tonga eruption. So this is the image taken from the satellites. And you can observe the immense nature of this ash cloud and the area that it ends up covering. It is humongous. The height could reach up till 100 kilometers, thereby disturbing the atmospheric balance in any particular area. And in these clouds, ash clouds, there are a lot of particles which are there, right? Now, this ash cloud will have particles which are electrically charged particles. Okay. Now, these charged particles basically become one of the major generators of the lightning. Okay. So, that is why you will observe that in this ash cloud, almost every second, hundreds of lightning events they do take place. So, ash cloud is very well known for lightning. They will also bring rainfall, obviously, because amongst the gases which are released by the volcano, which are the gases? The gases are nitrogen oxides, carbon dioxide, sulfur dioxide. But one gas which is released in majority amount is actually water vapor. This is released in large quantum. In every volcanic eruption, water vapor is one of the most dominant gas which is released. So that is why this ash cloud brings rainfall. But the rainfall will have the presence of ash also, isn't it? Various different chemicals will be there, various different elements will be there. So that rainfall will have the nature of an acid rain, which can again impact the species in the surrounding area. Okay. Now, then we come to the types of volcanic landforms as are mentioned here. So there are different types of volcanic rainfall. Yes, acidic rainfall, because why? Think about it. This nitrogen oxide will react with H2O and will produce nitric acid, HNO3, nitric acid. Okay. Then this sulfur dioxide will react with H2O and will produce sulfuric acid. Okay. So that is basically, yes, carbonic acid also will be produced. So as a consequence of that, when the rainfall does occur, it will bring around substantial amount of these acids along with them. Now we come to the case of the various different landforms which are created as a consequence of a volcanic eruption. So here, different types of volcanic eruptions occur. NCERT does not mention all the types of eruptions, so we will not discuss all the types of eruptions. We will discuss the type of eruptions which are present here, mentioned here. One is what is referred to as the shield volcano, right? They are with low pH or not. If it is nitric acid, it will be low pH. But yes, it is not a very concentrated nitric or sulfuric acid. It is slightly diluted. Okay. Anything which is acidic means it will have a pH value less than 7. Anything which is acidic will always have a pH value less than 7. Okay. Now, here, when we talk about the case of the shield volcano, shield, where does the name come from? So the name is basically derived from the shields and the swords that you have. Now, in the shields and the swords that you have, what is the characteristic of a shield? Almost featureless with very low gradient. That is how shields are. So this is a volcanic landform which doesn't have very steep slopes. It has got a kind of a gentle gradient out there. Okay, so that is what is referred to as a shield volcano. Now, how is this shield volcano created? So, a shield volcano is created when the lava which emerges out of that volcanic eruption, that lava is has to be very fluid. It has to flow almost like water. Okay, so that is basically, these will be created whenever you have the case of fluidic lava. Okay. Only then, if suppose here the eruption is happening, the lava will tend to flow almost like water and will create large sized landforms. Okay. That is the nature of the shield. very famously in the area around Hawaiian Islands. There you have Mauna Loa, Mauna Kea. These are basically your shield volcanoes, some of the largest shield volcanoes across the planet right now. Then, even when we talk about the Deccan traps in our country, they have been created as a result of this shield volcano. Deccan traps in the country, which are present in Maharashtra, Karnataka, in all these areas, it has been created by this kind of a fluidic lava. Then, when you talk about the Canadian shield in Canada, northern portion, there you have near the Laurentian Plateau. Even in Africa, you have the shield. So many of the continents, they have this shield volcanoes which are actually present. Okay. Now, when I say fluidic lava, what types of lava are actually out there? So you will find that there are different types of lava. But first of all, which areas are prominently known for the shield volcano? One is the region here, that is Hawaii. Hawaii. I hope we can see the background map here. One is the region here. This is your Canadian shield. Canadian shield. Okay. Then you have the region here. This is your Deccan traps. Okay. Then you have an older area here. This is known as the Ferro Scandian field, which basically had led to the formation of the present day Norway, Sweden, Finland, those areas. Eventually, more eruptions happened, and then you had the mountains. But initially, a shield eruption did happen. Then you also have the region around here in this area and in this area. This is the region of the Wall Shield, also known as African Shield. Okay. So, like that, you have multiple shield volcanoes across the various different regions. Okay. Now, this is the schematic representation of Mauna Loa. So, you can see what is the width of this entire shield. The width of the entire shield is how much? It is around 180 kilometers, which is huge, right? Think about a single volcanic vent creating a landform which is 180 kilometers wide. So, what will be the feature of this shield volcano? A quick recap and a quick revision. First of all, fluidic lava, fluidic lava. Then, after that, low gradient, that is gentle slopes. Okay. Then, after that, larger area. Now, what about the height? Will the height be massive? Not always, right? Height can also be limited. Now, because the lava is generally fluidic, yes, so the eruption will also not be explosive, but we will come to that when we study the types of lava. So, basically, when you take a look at the types of lava, there are different types of lava, but in a very generic term, in a very simplistic term, not going into acidic, basic, etc. Let us come to the visual appearance. One is this type of a lava that you see. Another is this type of a lava that you see. Okay. Now you can see that in the first one, obviously, the flow was much greater. In the second one, the flow is not so massive, isn't it? In this image, you will see or in this graphic, you will see the lava which is indicated. It is not flowing, as is the case of the first one. First one is flowing almost like water. So you basically have fluidic, right? And you have viscous. This is fluidic, it flows. And this one is viscous, does not flow easily. Okay, tends to have a kind of a still like feature. It does not have a fluidic nature. So this is basically one where does not flow easily. Okay. Whereas in the first one, it is fluidic. Okay. Now, why will a lava be fluidic and why will a lava be viscous? It is dependent upon the materials, minerals, and the temperature. It is actually dependent on that. Okay. So, the fluidic lava, you will find that the temperature is much higher. Temperature is much higher. I will give you a chart also so that you can revise easily. Now, in this lava, you will find dominated by certain minerals, that is iron and magnesium. Okay, dominated by iron and magnesium, right? Now, here, the presence of the lighter materials which have composed the crust of planet Earth, that is silicates. Silicates, the presence is less. Okay, less amount of silicates. Geography should always be studied with the help of visual cues only. Otherwise, it is not a subject like history. In history, it is a kind of a story. But I argue that every subject has got the uh, basic scope of visualistic aspect. But in a subject like geography, unless and until you are able to imagine what a fluidic lava means, what a viscous lava means, you will always have the case of rectification. So I want you to have this image pasted in your memory. And whenever that fluidic lava is talked about, this should be the content which should come to your mind. Okay. Now, hereby, less amount of silicates. Now, imagine one thing. If a volcano eruption happens, okay, if a volcanic eruption happens where this kind of a lava has to come out, will that require an explosive eruption or will that require a non explosive eruption? If this type of lava has to come out, will that require an explosive eruption? Will that require a non explosive eruption? It will basically be the case of non explosive because materials are ready to flow. Materials do not have any resistance in themselves. So that is why this eruption is generally this kind of a lava, wherever it is erupting, it is associated with non explosive eruptions. Explosive eruptions. Okay. That is associated with non explosive eruptions. Okay. Whereas this kind of a lava, this lava, now again, another basic logic and a concept I want you to internalize. This lava that you are seeing on your screen, it is cooling down ever so slowly. So, can we imagine that while it is cooling down, there will be certain air particles, etc., which will be trapped between the layers also? Isn't it? There will be certain air particles here which will come in, here which will come in, and they will be trapped before solidification itself. So, when this lava will solidify, the rock which will be created will have less density as compared to this one. This is known as basaltic lava. Basaltic rocks will be created. And because iron and magnesium are dominated, this is also known as mafic. Okay. Ma, magnesium, Fi representing iron. Okay. Then, in this particular case, temperature is comparatively low, it is viscous, silica content is high. Silica content you will find is substantially high. Whereas, not always would it be porous. No, not always. Right. But in certain cases, definitely the porosity is associated with these kind of rocks. So that is a good deduction, Sudhanshu. but not always. You cannot have a generalistic, a sweeping statement made out of that. Okay. Silica content will be high. Iron and magnesium content will be low. That is why this will be referred to as felsic lava. Okay. That is the rock kind which are getting created are feldspar, silica, etc. So that is why also known as the case of felsic. Okay. Now, here the rocks created when it will solidify, the rocks which will be created, these rocks will be lighter in color because of high amount of silica. Just for your reference sake, so that you are able to recall it easily and understand it easily. When you take a look at the sand, okay, sand is what? Lighter in color. Now that sand is very rich in silica. Okay, it is that sand which solidifies eventually to form sandstone, etc. But that is what silica does. It induces a lighter color. So these kind of igneous rocks will also indicate a lighter color. And what about the density of these rocks which are getting created? This will be low density rocks. Okay. Whereas in the previous one, this kind of a lava, very fluidic, rich in iron and magnesium, the rocks which are created as a consequence of the solidification, these rocks will be of what? This will be darker color, darker color, and you will also find the case of these rocks being the high density. High density rocks will also be created as a consequence. Okay, because of iron and magnesium. Correct. Good. So I hope till now we are able to recall everything. I will give you a quick recap in the help of this table. Use this table to revise. Okay. So silica content, if the silica content is high, this is the one. Silica content is high. If the silica content is high, it is felsic. Temperature you observe is comparatively less, very viscous. Gas that it will trap will be much more. And for this viscous materials to erupt, it will require an explosion, isn't it? So the eruption will be explosive in nature. Whereas the silica content, if it is low, mafic, temperature is higher, fluid, it is fluidic, so low viscosity, non explosive. Okay. So that is the case of the silica content and its impact not only on the volcanic eruption, but also the kind of rocks which get created. This is not given in your NCRT in greater detail, but understanding the volcano is impossible without understanding this and internalizing this. So please refer to this whenever you are appearing or revising for the exams also. Now, then we come to the other kind of volcano which has been mentioned here. That is the case of composite volcano. Now, what is a composite volcano? A composite volcano is what is also referred to as a stratovolcano. Stratovolcano. Some of the largest volcanic landforms across the planet are created by this stratovolcano. Strato means what? Strato is derived from the term strata, which means layers. Okay. So that is basically the layers. So that is where, when you talk about the stratovolcano, it is the layered volcano. So what does the layered volcano mean? You will have an eruption, then ash, dust particles, etc. will set up. Then another volcanic eruption through this region. More lava will solidify. Their ash, etc., will settle down. Slowly and steadily, the size increases. Okay. So observe this animation and understand how the layer by layer deposition gets created. The reddish image that you see is your lava, and the brownish image that you see is basically your ash cloud which gets deposited. So observe this eruption, then in the same region the eruption keeps on happening. So first eruption will lead to the lava getting created, lava solidifying. On top of that, on top of lava, the ash will solidify. On top of ash, again lava will solidify. Like that, you will observe this formation of multiple layers, right? So this multiple layers which get created, that makes it very, very massive. Example, Mount Fuji in Japan, a very famous tourist destination. Then Mount Pinatubo in Philippines, which was responsible for one of the most explosive eruptions which has ever occurred in the 20th century. In the 19th century, Krakatau eruption. In the 20th century, Pinatubo eruption, which is present in Philippines. Okay. And then in the 21st century till now, you have the case of the Hawaiian and the Tonga eruption. Cinder cone is not a shield volcano. No. Cinder cone is a small volcano which gets created of a small height, which gets created when you have partially fluidic lava and the materials get deposited. They are much smaller in terms of their size. Okay, that is clear. Kilimanjaro is an example of an older composite or a stratovolcano. Yes. Okay. Now, some deviation from what the NCRT is talking about and some extra information for you. Over a period of time, this volcanic material will create so many layers, and these layers will solidify into hard igneous rocks. For the new molten material, it becomes almost impossible to break through these hard igneous rocks, isn't it? So basically, where will the molten materials emerge from? So many of the times, the molten materials they try to find a pathway where the rocks are weaker, rocks are older, okay, and they basically crack through the surface. And that is when the eruption can happen somewhere very far away. This is your volcanic pipe or the main volcanic vent, okay. This is where the eruption can happen if the main volcanic vent is blocked. This is what is known as parasitic cone. Cone. Why parasitic cone? Because just like a parasite is dependent on the host for its own survival. Now, this volcanic cone is dependent on the magma for its entire eruption. That is why parasitic cone. Okay. Now, then we come to another kind of volcanic eruption or a volcanic landform which gets created, and that is what is known as a caldera. The image that you see is that of the Tonga eruption that I have been talking about. Now, what is a caldera? Now, I want you to observe this image carefully. Manikaran geysers in Himachal are linked to this process. Absolutely not. Manikaran, the geysers that you have in Manikaran, the hot springs that you have in the region of Ladakh, they are not associated with volcanic activity. Why do you have geysers and hot springs in the region of Himachal and Ladakh? Is basically because of the simple fact that there the rocks are getting compressed in leading to the formation of Himalayas. That compressional heat is so very high that in certain areas the groundwater gets heated beyond the boiling point, and that is when it is exposed to the outer atmosphere, immediately it gets converted into steam like condition. So that is generated because of what is referred to as the compressional heat. It is not generated because of the magmatic heat. Okay. It is a basic kind of idea about the region of geothermal energy that we talk about in geography. Now, coming back to the topic, I want you to observe this image carefully. Now, here, what do you observe in this place? You will observe there is a kind of a collapse, isn't it? There is a kind of a collapse, which is initially explosion is happening. And then after that, there will be a kind of a collapse, right? So there are certain volcanic eruptions where the central portion after an explosive eruption simply collapses. That creates certain kind of landforms which are known as caldera. So when you observe a caldera does appear to be like this. In many of the areas, it is the sea water which will enter the gaps of the collapse. But in inland areas, you can have a feature like this. So, what is this? Imagine at one point of time, this would have had a shape of a mountain feature like this. The central portion has collapsed. Okay. Later on, filled by the groundwater or by the case of the seawater. So, let's take a look at the caldera once. One of the most explosive, one of the most explosive of the Earth's volcanoes. They are so explosive that when they erupt, they tend to collapse on themselves rather than building any tall structure. The collapsed depressions, they are associated with, they are known as calderas. Okay. Now, their explosiveness indicates that the magma chamber is not only huge, but also in nearby vicinity. Okay. So, basically, understand this. You have read the text, you have got the definition. Now let us understand it in a visualistic manner. So, what happens? Let us understand in a stage by stage manner. This is your volcanic eruption. This is the case of your volcano. Okay. Now, just a moment. Yeah. Now, this is the case of your volcano. Now, here you can see the magma chamber which is present in this. Magma chamber is present. Now, this magma chamber will lead to explosion, as you can see in the second image, a very explosive eruption. Now, in that explosive eruption, it can also happen that the magma chamber becomes completely empty. Every material gets out, right? And it is so explosive that it weakens the entire, you observe the third image, it weakens the entire crustal region. Now, the underlying portion is empty, the surface is weak. What will happen? Central portion will collapse. So basically, if you had a volcanic landform like this, okay, and let's assume this was basically supplied to a magma chamber. Now, this magma chamber in one of its final eruptions has basically emptied itself, empty. But the eruption was so very massive, so explosive, that it created multiple cracks in this region. Okay. Now, after that, the underlying portion will become absolutely empty. So the weight on top is too high. So that is where the central portion will simply end up collapsing. So the landform that you get as a consequence of this, the landform that you get as a consequence of this will be somewhat like this. I hope this is understood. That is the entire process of formation of a caldera. Calderas can be very large. Now, one simple question I will ask you. In these calderas, can the future eruption of volcanoes happen? Because the magma chamber is empty. Can it be the case that in future the volcanic eruption can again happen? Let me know in the comment section. If yes, why? If no, why not? Then we come to another kind of eruption, that is the mid-oceanic ridge eruption. This is the kind of volcanic eruption which occurs underneath the oceans, in areas underneath the region of the Atlantic, for example. Okay, almost in the entirety of the region here, Indian Ocean also, in the region of the Pacific also. So you will have these underneath the oceans. So what happens is that underneath the ocean, molten materials, they emerge and they spread. This is known as the mid-oceanic ridge. Why the name mid-oceanic? Because generally present in the region of the oceans. And why ridge? Ridge is this kind of the shape. Ridge can be present on land also. Ridge is any area where you have a certain height associated. That is what is a ridge. Okay, so over land also, near Delhi, you will come across the Delhi Ridge, Aravali Ridge, Delhi Haridwar Ridge. Okay, so ridge is any region where you have a kind of a uplifted land feature which is not exactly like a mountain. Okay, but then nonetheless, it is having a height. So this is what a ridge will tend to look like. Okay. So this is the land ridge. So it happens underneath the water. That is the mid-oceanic ridge, which is created by underwater volcanism. Okay. Now, so basically, in the case of the question that in the region of calderas, can eruption happen? The answer is yes. In future, if let's suppose you have the magma chamber which again gets filled up, so in those cases you will have the future eruption also happening. For example, if you take a look at the Italian coastline, in Italian coastline you have a region that is Mount Vesuvius. Vesuvius is a name you would have come across whenever you would have come across Pompeii, for example. Pompeii is a horrific story. All of you would be aware about the story of Pompeii, whereby in around 78 AD, a volcano completely flooded the region with lava, and multiple people, the entire city was immediately converted into stone, right? You had various different skulls and the region of the brain getting converted into glass like crystal. It is still preserved as a UNESCO World Heritage Site. So, that is the region where Vesuvius was an ancient caldera. And over a period of time, the magma chamber got filled up. And within that caldera, multiple eruptions did happen. So calderas can be very, very large and can have multiple such eruption within them. So Vesuvius is situated within a caldera. If you have to give examples of caldera, by the way, what are the examples that you will provide in the exam? One is the case of Crete in Greece. Other is the example that you will provide of this, Tonga in South Pacific. Okay, South Pacific. So in this image, what you observe is the Tonga eruption was created by one eruption here, another eruption here. It started with 2015 itself, when an island was created. But in 2021-22, such a massive eruption happened that the entire region collapsed and seawater entered it. That is what is the case even in Crete, in the region of Greece. By the way, we also have a very old caldera, example of caldera in India, and that is present in the region of the Aravalis. When you basically drive down from Delhi to the west, as you cross the region of Pataudi, you would have heard about Nawab of Pataudi. So that is where you will find the evidence of old caldera, which was possibly created roughly around 2 billion years ago, when India was not the size of the land that you see today, and India was in a very different position altogether. Okay, so that is how calderas can get created. Okay, now overall, these mid-oceanic ridges, they are present all across the world, and they form one of the longest continuous chain of landforms, roughly around 70,000 kilometers. Think about it. Andes, one of the longest mountain ranges across planet Earth, around 8,000 kilometers. Mid-oceanic ridges, almost around 70,000 kilometer. Okay. Now we come to the portion which is given in your NCERT. That is the last portion. That is the case of intrusive volcanic landform. What is that? So when we were talking about the magma and the lava, please understand that when you have the molten materials, if molten materials emerge and erupt from the surface, right, they will form rocks there, volcanic landforms like a composite volcano, a shield volcano, etc., a caldera. See, observe here in this image, you have a large older caldera and a new cinder cone. Okay. So that is also observed, by the way, this kind of a feature you will also observe in the case of Mount Tal in Philippines. Why I'm telling you these examples is because when you are writing your answer, very important to retain these examples so that you are able to produce that in your answers also. So if molten materials they do emerge from the surface, they will create these volcanic rocks which are on the surface, right? These are known as extrusive volcanic landforms or external volcanic landforms or simply volcanic landforms. But sometimes you will find that this molten material is unable to break through, right? It is unable to break through. It solidifies over a period of time. And that is when it solidifies over a period of time. It is exposed much later when the top surfaces have been removed. And that is what you have as the intrusive volcanic landforms. Always a caldera will be much larger than a crater, volcanic crater. Okay, always caldera will be larger. Now, this case of the solidification which has happened, it has happened in the interior of planet Earth. That is why named as intrusive volcanic landform. Now, one unique feature of the intrusive volcanic landform you will come across is the fact, how do we know whether a landform has been created underneath the planet Earth or not? Over large period of time, all this will be eroded, weathered, and removed, right? The rivers, rainwater, everything will basically remove this. Okay. Now, at that point of time, these portions will be exposed. Then we get to know that yes, these are the landforms which have been created. Okay. Example. One is the case of batholith. What is a batholith? So when you have the entire magma chamber in itself which solidifies, solidification of magma chamber, magma chamber. The entire magma chamber, when it solidifies, you will have the formation of batholith. And later on, when they are eroded, so imagine if this entire magma chamber, if let's suppose it has solidified, the top surfaces are so old they have been eroded, then you will get to see. So this is your batholith. So imagine at one point of time, on top of it, lot of other land would also have been present. Example, in Jharkhand, in the region of Ranchi, right? You have the region in Ranchi, famously known as Ranchi Batholith. So, in that area, you have in Ranchi, you have something known as the rock garden. So, that rock garden is nothing but the exposed magma chamber. That is basically the part of the older Chota Nagpur plateau. So that was a part of the ancient magma chamber. Today, you will find a very smoothened shaped rocks to be present in those areas. In Karnataka plateau also, as you move from the region around Ramnagara onwards, uh, uh, down off the Bangalore plateau, there also you will find some of the evidences of the older batholiths. So batholiths are basically your solidified magma chamber. Then you have laccoliths. What are laccoliths? Laccoliths are your flattish in shape, may be connected to the old magma chamber and a cone shape on top. Over a period of time, they get exposed like this. This is a laccolith. You will find this in the region of western Tamil Nadu, right? In the Bangalore Chennai belt, in the region of western Tamil Nadu, you will find this kind of a appearance and the kind of the landform. Then you have Lopolith also. What are lopoliths? Lopolith, if you observe, so the difference between laccolith and a lopolith. So basically, laccolith is somewhat like this. Lopolith will have a flattish top and a convex bottom. This will be your laccolith. This will be your lopolith. Here, when you see lith, lith basically refers to rock, the name from where you get lithosphere. So lith basically refers to rocks. Then you also have faccolith. What are faccoliths? Faccoliths are when the solidification happens in a curvilinear manner. So here you observe this, okay, in this manner. That is the wavy appearance. That is the case of a faccolith. So let's suppose the solidification of magma has happened in this region, or in this region, or in this region, right? That is the case of a faccolith, okay? Then you have sills and sheets. Whenever magma solidifies in horizontal region, that is known as sill. Here you observe this image. You observe that this particular layer of rock. This is not nothing but a very old solidified magma. This is what is referred to as sill. However, if the solidification has happened in a very thin manner, very thin, that is what will be referred to as a sheet. So sills are thicker, sheets are thinner. Then, if solidification has happened in a vertical manner, observe this, vertical manner, and that has remained in the interior itself, those are known as dikes. So, at one point of time, imagine the rocks would have been present like this, they have been eroded, they have been weathered. Okay. So, over a period of time, everything here has been removed, everything here has been removed, and now you have this almost vertical column. These are very, very rich in minerals because they experience such high pressure that crystallization does tend to happen. So, even for example, diamonds are extracted from the ore that is kimberlite. Now, much of that kimberlite is to be found in these kind of dikes. Okay, so a very quick recap of this intrusive volcanic landforms. Intrusive landforms, what are those? So, based upon the shape in which the solidification has happened. So, you have batholith, where the entire magma chamber has solidified. Then you have the laccolith, flat base and curvilinear top. Then you have lopolith, flat top, curvilinear base. Then you have faccolith, a kind of a topsy-turvy shape. Then you have sills and sheets, right? Sills are thick, sheets are very thin. and then you have dikes, vertical. Okay, I hope that is clear. Big Bang was explosion. Later, immediately after explosion, leading to expansion. Okay, so this is where we'll restrict the session here today. And I do hope that we have understood it. Tomorrow is going to be a very important session, important for your prelims and the mains examination. Tomorrow, we are going to have a discussion of the origin of continents and the oceans with the help of continental drift and the seafloor spreading theory. So, that is what we are going to discuss today. If you have liked the session, please don't forget to click on the like button, share it with your friends, and do subscribe to the channel and put that in the comment section. And we meet again tomorrow. Till then, do take care. Goodbye. Thank you.